So welcome everybody. Before I introduce the speaker, I would just like to say that next month's meeting, which I think is on the 18th of June, we'll be having the second half of Troy Bernier's talk on hyperspectral remote sensing and mineral identification. So I think that will be very interesting, and he's going to give some really good practical examples of what it can do. So Brian Hunt has worked for many, many years in Central Texas, principally for the Barton Springs. Am I right, Brian? The Barton Springs
district. That's right, a groundwater district. For
giant long acronym. So he's done 20 years of mapping groundwater in the Edwards Aquifer and its contributing zone and so on. And he's now working for the Bureau of Economic Geology here in Austin, principally making geological maps for the Bureau. And anybody who knows the mapping situation in Texas knows that a very, very tiny proportion of the state has been published. Geological maps of a very tiny portion of the state have been published at any reasonable scale. So Brian is helping to remedy that deficit. And he's going to talk about all the modern methods that are now used to expedite and efficiently achieve this expansion in large-scale geological mapping in Texas. So let me hand over to Brian.
Okay, can you all hear me all right? Okay, well, thanks, John. Appreciate the invitation to come and speak to you guys about a real passion I have, and that is making geologic maps. And as John said, my first career was as a hydrogeologist and did a lot with that, but always tried to connect the rocks to the groundwater system. And so I've been able to come to the university just 3 years ago. And I just want to acknowledge, I work for this great team. Jeff Paine manages the overall mapping program, and Chuck Woodruff and Mark Helper and John Andrews form the team, as well as a couple others here at the Bureau of Economic Geology. And the Bureau of Economic Geology is really the state geologic survey. And so you can think of it like that. That's one of its roles is that function. And so it's, of course, associated with University of Texas at Austin. We're kind of the research arm of UT Austin. And so so with that, I'm going to talk about, this kind of transitional period that we're in. Many of us learned field methods and all the mapping techniques and the tools of the trade. And I came in just 3 years ago, and some of this was new to me, and it's old hat to many of y'all, I'm sure, like GIS, for example. But we're in a transitional period, and so I'm just going to talk a little bit about that. And so before I jump in, just wanted to thank a few folks, and that including Jeff Paine is the main PI for the mapping program, but also the USGS folks. And I'll be talking a lot about the geologic mapping program and the schema that they've developed. And funding for all the state maps in Texas, or the geologic maps in Texas, are funded through a federal program called State Map. I'll mention that a little bit, and also and matched by state dollars, the STAR program. And there's certainly lots of colleagues and that provided support, and in addition, landowners out there that allowed me access to go stomp around, and they see real value in the geologic maps. And that's kind of what I also just want to remind all of us, although I'm sort of, preaching to the choir here. And I guess I would say, what is the value of a geologic map to somebody out in the field? And because that's kind of one of their questions often is, what is this used for? And I try to, when I go to the field or I'm working in an area, I really tie it back to resources like groundwater, because that's what I'm most familiar with. But it's also what most of the rural folks and ranchers and everybody has a well, and they want to know where the water is. So tying the maps to that resource in particular has been very effective. But as you all know, really geologic maps are the primary and critical data set for applied earth science investigations. And so in my example of groundwater, but certainly of engineering or other types of hazard type investigations, it's fundamental, and you really have to start there. So those are all things that I know we know about. So as John alluded to, I've got some job security here. There's only about 7% of the quadrangles, that is 1 to 24,000 areas, have been mapped in Texas. So compare that to about 20% in the rest of the United States, lower 48 at least. And so now we all know that there's probably large areas of Texas that don't need that level of detail, the 1 to 24, but the word detailed really means anything sort of larger than 1 to 100,000. And so 1 to 100,000 scale map, the 1 to 24, those are detailed geologic maps. And when we think of, we think of detailed versus, what's the opposite of that? It's sort of a coarse or small scale map. So all of Texas is covered by the Geologic Atlas of Texas. These are 1 to 250,000 scale maps. So they're small scale because 1 to 250K is a fraction. So it's a really small number. So think of it as a small scale. Those were published in the 60s through the 80s. And when I mentioned detailed maps, and that's really what we're making, they're really much larger scale, and that is 1 to 24,000. And we produce these open file maps. And one point, when I say detailed, now it sort of takes on another connotation, because behind the map you see on the right, is a database. And so each line, polygon, and point has tables of attributes, as opposed to, a paper or even a GIS coarse scaled map that may not have that level of detail. So really, these digital geologic maps are really map databases, and that's kind of a key point. I'll talk to y'all. And also, this is I'm kind of going off track here, long introduction, but also, I've been mentioning these scales, 1 to 24,000, 1 to 250,000. And, the new maps we're making now, these digital maps that rely on, GIS, they are really, it kind of begs the question of is scale really relevant? Because if they're created in sufficient detail, they could be really almost any scale you need. So that little yellow box, that's 1 to 5,000. So that's a 1 to 24,000 map that I produced. Yet me as a mapper, when I was zoomed in or looking at data, I was often at a much different scale. And so for detailed maps, I think scale is kind of an irrelevant thing, but that's a little bit, offline. So here's really the outline of the talk. So I just wanted to mention a little bit about the history of geologic mapping in Texas, touch on the mapping program, and really kind of get to the meat of what I think has changed, kind of the mapping approach and some of the tools, and a little bit on the workflow, and try and use some recent examples, and then kind of summarize things. So the map here on the right is a recent open file map that we produced. And so really the talk is, how did we make that? How did we produce that? But let's, step back in time a little bit, just for context. The first geologic map that we've all kind of learned about was William Smith in 1850. And so you just kind of help sort of calibrate yourself. If we step over to Texas, the first geologic map that I'm aware of was a German who came in the 1840s. So, not long after William Smith published his map, he was publishing a map of Texas, and I think that you can see there's like five units, and you can see the Llano uplift. So he kind of got that right as a unique feature in Texas. 1880s to 1900s is R.T. Hill, and R.T. Hill is really known as the father of Texas geology. He was a professor at the University of Texas, and he really created the department. So here's a map that he produced in 1902. It's a really amazing map, because you lay a modern map on there, and really all the elements are there. And so the progression and knowledge and mapping techniques were really rapid. So the BEG was, that is the State Survey of Texas, was really formed in 1909. And at that point, they ushered in, an army of geologists, so to speak, Sellards and others in the 1930s. We produced this Stratigraphy of Texas, just kind of big Bible that defines and describes all the geologic units. 1940s and 80s were the era of Virgil Barnes. And if you were a geologist in Texas, you really know that name. He mapped most of the entire state, lived to be 100 years old, was still working in his 90s at the Bureau. I unfortunately didn't get to meet him, even though I'm old, but I just didn't quite overlap. When I was a student at the university, I'd heard of him, but Barnes really dominated the scene and was prolific in the geologic quadrangle maps that he produced. And he also oversaw the Geologic Atlas of Texas that covers the entire state. That's the 1 to 250,000 scale. But he also produced lots of detailed quadrangle maps. And then more recently, Eddie Collins, who's now retired, but Jeff Paine, again, the PI for the mapping program, and others produced maps, and they kind of ushered in the age of GIS. And so so Jeff in particular has bridged that gap of, or that technique of just pen on paper into GIS, and now the new map database that I'll talk about. And so this is kind of where we are. And I guess one of the key points I want to make is, I'm new to this. And so people have been using GIS a long time for geologic mapping. But in 2020, the USGS published their geologic mapping schema. And that is really the standards for the database that's behind modern geologic maps. And so here's kind of a screen capture of LiDAR, but you'll see these tables. It's the screen capture of GIS. And so this is the new map. These maps are not static, they're databases. And so that's the big shift, I would say. And so as part of the mapping programs, which I'll get into in a second, if you accept funds from the USGS to produce maps, you have to make maps according to this standard. And so this is the big shift. And so I'll talk a little bit about that and implications for that. So here we are, just to remind folks about, the U.S. Geological Survey has been making geologic maps for a long time. But in 1992, the National Geologic Mapping Act mandated the development of the National Cooperative Geologic Mapping Program. And what that really did was sort of create the vehicle for the USGS, the feds, the federal government, to collaboratively work with state geologic surveys. And so with that, their very first project was to inventory all the maps that were out there. And the BEG has been working with the National Geologic Map Database since 1996. And again, we've been accepting federal funds, the state map funds, and matching it with state dollars from the State of Texas Advanced Resource Recovery, or STAR program. The second phase, so the first phase of this after 1992 was to inventory all the maps, create a online database so you can get access to all these maps. The second phase, which again just was published in 2020, was to develop the standards, the map database standards, and that's the GEMS, Geologic Mapping Schema. So here it is. This is the standard. I'll come back to that. So back to Texas, again, we have an active mapping program. We have sort of 4 areas that we concentrate on. The first area is the Gulf Coast. It's divided in kind of a northern and a southern, 1A, 1B, but we've got Jeff and Tiffany Cobble are the mappers along the Texas Gulf Coast. The second area is Central Texas. That's what I'm doing, and that having to do with water resources. And the third area is along the I-35 corridor. So this is a high growth corridor right in here, and Woodruff is doing that. And then critical minerals out west. So those are our 4 kind of concentrated areas. And so every year we come together, and I should say the little yellow squares are what's been mapped. And so you can see there's been a fair amount of work done. although a lot of those are just paper maps, right? They're not up to the new GEM standard. And then the sort of colored little rectangles you see are the active or recently published maps. So we internally at the Bureau, the State Survey, we get together and we propose every year to the USGS, our priority mapping areas. And so we get feedback from from an advisory committee about those areas before the proposal goes officially to the USGS. So we get feedback from other folks, other agencies in Texas, to be sure that we're doing things that are of interest and value beyond just us, and we're not missing something. So this is part of the proposal process. And I should say that all these maps that I'll mention are available at the UT Bureau of Economic Geology store. It's really difficult to find a map there, though, I have to say. And so they are developing a new interface to be able to find maps. But to really find a map, the best thing to do is go to that National Geologic Map database in this map view here. It'll take you to a map viewer. From that viewer, you can select a scale of map that you might be interested in. And I've highlighted one here. That's a quadrangle scale map that is right here on the right. This is one we published in 2021. So this is where you can find all these maps. So let's get to the meat of it, is really the mapping approach, the tools and workflow. What's changed and what's different? And and again, these are my observations, and I'm kind of new to it, and so some of these things may be just kind of obvious to some who've been doing this for a long time. First off, we know that geologic principles haven't really changed, and so the law of superposition, cross-cutting relationships, all of that. Of course, that's not really what I'm talking about. Field methods, though, have started to evolve, and what I learned. John, is your screen still there? My screen just went blank.
Yes, it's still there.
Okay. All right. Well, I have one of them. I can still go. So field methods, as we all learned, with Compton, probably many of y'all had that for your field methods class. Those have really evolved to include things like GIS and GPS and other technologies. And I think we've taken a really big step even more recently. So in the old days, it was, really, say old days, I participated in this, field camp was very much very analog. The methods we learned, the tools we used Bruntons, we had paper, we would go out in the field. This is actually Mark Helper, 1995, when I was in field camp, and an example of a field map. And so the tools have evolved from purely analog to something that's a lot more digital and analog as well. With the primary tool really being GIS, and some of the data collection techniques with iPhones don't use a Brunton anymore, or GPS. Still use a field book and hammer and hand lens, but and again, maybe a lot of this is really not new to you all, but the way fieldwork has evolved is kind of new to me. And I'll just say that in the old days, I keep saying that, but previously, before the sort of the digital revolution, when you would go make a geologic map, you go out in the field, you would create your map, and you really wouldn't leave the field till that paper map was done. And so now with GIS, you can create a map before you go in the field. So your field work now tends to be a lot more focused. I'm going out to very specific locations to, field verify, or if I'm unfamiliar with stratigraphy in this area, to go and learn that stratigraphy and how the geomorphology looks in that particular area, verify problems or test hypotheses, that sort of thing. So, I still use a book, but really going out in the field, it's really in your iPhone or your smartphone. And you can use, all these different apps. I typically use Avenza for creating a map and then carrying it with me, and it shows me where I am on that map. And I can take data points. I can create lines, and they can have attributes. I can attach photos to them. At the end of the day, I can email a KMZ or the notes to myself, and I can pull them up into the computer. The Brunton, I no longer use a Brunton. I still carry one, and occasionally we'll verify, what I'm measuring with my phone. But you can measure so much more precisely and quickly if your phone is properly calibrated. That I just don't even use that anymore, and I'm collecting far more data than I did before. There are very advanced apps to use, like StraboSpot. I haven't used those yet. I just use these two primarily to collect data. And again, I get back to the primary tool, the mapping revolution, and of course, not news to y'all, is GIS, and it allows you to analyze and transfer and archive all the data and all the data behind each of these lines and polygons and points. That is the attributes, and so that's the key thing. The map is no longer, and if I've said it once, I hope I did, that geologic maps are really no longer these static two-dimensional things. They are databases, and if they've been developed according to the GEM standards. And so here's an example of a portion of a map, this screen capture of using ArcMap. Here's a feature, and then here's a contact right here. So this highlighted contact is a contact. It's not a fault, and so it has all kinds of attributes that you can see. The location confidence is about 30 meters. The existence confidence is certain. The identity confidence is certain, meaning I know it's a contact and it's not a fault. The data source, so this DAS number 62, that's really a reference number. So that's back to Barnes and Schofield 1964 or something like that. Anyway, there's a lot more attributes, as well as other comments you can make about a particular line or polygon or point. So points are the same way. Here's a strike and a dip. Not only are the numeric values in a table, as well as all the other sort of attributes that I just mentioned. Many other types of data can be put into a map now. Things like fossils. These are locations. These are measured sections on this line here, with these little dots are actually fossil sample locations that were on a 1946 map. But now they're in this database. They have the locality number. They have the type of fossil form. They have all kinds of information that you can now query and discover. Addition, you can add other feature classes if you have geochronology, for example, or springs and wells, or other types of data that would really complement the geologic map. So it now has the container for all of this. And so, lastly, I talked about GIS being and GPS, I should say as well, are really revolutionized making geologic maps. But I would say really right up there is LiDAR, and that is light detection and ranging. Everybody, I think, knows what LiDAR is. Remote sensing method uses light to form in a form of a pulse laser to measure, the ranges. So you can create a bare Earth model. You can strip away the vegetation and see what the Earth looks like. And that is now, I would say, in Texas, is fully covered with LiDAR. It's got various degrees of resolution, but it's all actually quite good. I'd say it's really a fundamental and essential base map element now, that I couldn't really be doing what I'm doing without it, at least to my satisfaction. So that's been a huge step forward, I'd say. And just to prove my point, here's a screen capture of, this is the middle of the Grit quadrangle is what I had mapped, my first quadrangle. So this is that same area with a map from 1964. This pattern is basically metamorphic rock. This is a lens of marble, and they use red for marble. I don't know why. And this red over here is a granite. And so you can kind of see that little gray area and that marble. And this is, pretty apparent on most aerial photographs. But I used LiDAR, and again, I use LiDAR as really the fundamental base map element. And I don't use just the elevation as a gradient. Often what I do is I create a shaded relief with some vertical exaggeration. And then we'll put an arrow, make this aerial photograph transparent. And then when I do that, this is what pops out. And what you can see, this is the very same area. Here's that road, that highway right there, right? And what you see is this big structure right here. This is a big aniform. So not recognized, without LiDAR, you just would never see that. That's about a mile in length right here in this very large feature. And so here's what the geologic map looks like here. You can see this aniform. And if I make the if I make the geology transparent, you can see the shaded relief coming through with the geology on top. But again, LiDAR really made all of that possible, as well as mapping quaternary, which I'll share with you. So, again, before you go in the field using LiDAR, using existing maps, you often create maps and it'll focus your field work. And so, using my app, and the map I had created, here's that big synform, and these little points are the places I visited. So I had mapped a fault through there, and sure enough, there's big fractured rocks. But when I went to this big aniform structure, what it turned out to be was a huge quartzite. So these are Precambrian rocks, Grenville age. These are quartzites, but they're crossfed. And so it was really an amazing thing to be able to I guess, laser in right exactly where I needed to go using LiDAR and the approach just talked about here. So that's really the key elements here that I wanted to bring up. And then I'll sort of show you some field examples. But if I were to just sort of think about what is the workflow to produce a geologic map over a year's period, and that's the time period I have, is a year to create actually 3 to 4 quadrangles. These first two phases are really what we're talking about. The first phase, you spend a couple months just creating your base map. Is getting your LiDAR, your historic maps, other data sets all together. You create your GEMS database in GIS. They're your containers that are going to hold all these. And again, those containers are highly specified through the GEMS USGS publications. And the field work, and it's very iterative, you go back and forth, but create these your lines and polygons and your data sources and your description of map units. You spend, most of your time doing that. It's iterative between GIS and field work. I don't go out and just do it all. It's back and forth. The third phase I don't really talk about here is really kind of crossing all the T's and dotting the I's according to the GEM standards. And that's where you're running scripts and trying to really complete the database per their standards. And then the final step is really the layout. And that's just using graphic software like Adobe Illustrator. And you're doing that really according to your own internal standards or map layouts. That's where there's some geological review, there's some editing going on, and like layout work. So we're really just talking about these first 2 steps and what's really changed. Okay, so we'll get into a few examples, and I just wanted to show you all some screen captures of this is, in Central Texas, we have the hill country. We have all these limestone units that blanket everywhere. And so using LiDAR, again, you can map these sort of pancake units using a slope map or using the LiDAR itself. And you can see just how visually you can see the contours in here as well as the hill shade. And this is what that standing, I was standing right here, I took this picture, and you can see these breaks and slopes correspond exactly where these GPS points were that I collected with my iPhone. And then sketch some notes here about those units. So you can really use LiDAR for mapping these types of structures. I sort of mentioned the quaternary, and I've never really mapped quaternary, but out in West Texas, there's a deeply incised canyons out there in the Edwards Plateau. So these are flat-lying Cretaceous age limestones. And in these canyons are deep deposits of quaternary, alluvium and terraces. And you can see here by using LiDAR, you can create the hillshade, which is what you see transparent through the elevation gradient. That is the color that you see. And so you draw a line using, again, GIS, you can see the terraces that are developed. You can start to help yourself map. This would be like Q3, depending if you're counting terraces going up or down. Maybe this is Q2 and Q2 over here. And so, again, LiDAR gives you the ability to map these types of things that otherwise would be relatively difficult. When you look at historic maps, they typically just map the whole thing as QAL. And that's really not the story that we see here. Another really good feature of LiDAR, this is a good example. This is out the same area. This is Dolan Creek. So that same creek I just showed you, you can see these stacked limestones here, is you can use LiDAR to find closed depressions or karst sinkholes, or at least potential ones. So you can do some manipulation of these bare earth models to basically show you where water won't drain out, and you can then color code those to their depth. And then, for example, here's a big red deep hole, and sure enough, when you go there, that's actually a cave right along a bedding plane, and there's evidence for a recharge that's occurring there. So a really useful tool that you just couldn't go to. You couldn't cover the whole area without the advent of LiDAR. And so even on the upland plateaus, when you get up high, this is well above maybe 300 feet up on a plateau, there's a little hint here of a closed depression. And I was at this well, so we walked over there, and sure enough, what did we see was a big, solution cavity that went down. So really impressive for mapping those types of things. So that's kind of using, LiDAR fundamentally as a tool for mapping. What's really interesting and fun is when you get to use historic maps, the LiDAR and the aerials, and you're really compiling it all together. And that's really what I am, I'm a compiler. Folks have done really the hard work of making these amazing geologic maps. I've got the benefit of technology or other data sets that I can sort of mash them together and try to make the best map I can. These are two examples of the kind of maps or data that I've used to create a map. And so in Mason County, which is Central Texas, where I'm mapping, here's an example of, these are two quadrangles that are just about to be published. And you can see there is a veritable quilt of theses from the 1950s primarily that cover these two quadrangles. So it was a real joy to try and look at these maps and use them the best I could. So here's an example, the Mason quadrangle. Here's one of these theses, and here's the map, 1952. And here's the field area that I was going to show you. So this is an aerial photograph with that shaded relief coming through, so you can see the hills, right? You can see what clearly are faults that are coming up through there. Here's a highway. So when you pull those maps into GIS and georeference them, and they don't fit. Those are all planimetric maps. They didn't really have a base map, but there are key features I can try and fit them into real space. And so you use these maps. You can make them transparent. Wash them up and down to build your modern map. And so here's the modern map. This is the GIS map that's about to be published. And you can see all these structure points, which again, all these polygons and lines have attributes. So they would point back to this map, whether it was that data point, or if I mapped a fault right here, that used it, and I used LiDAR to maybe modify Alexander's interpretation. That data is there, and you can certainly see all the different geologic units. So there's an example of using these historic maps that is really a lot of fun. Additional added value for published maps. Virgil Barnes, again, the father of modern geology, I think, in Texas. He published 1978 a geologic quadrangle map around Johnson City, and they did have base maps there, and they're very good maps. They're excellent maps. On the left, you'll see a portion of that map. This is the Pedernales River. You'll see two mapped faults with these other Cambrian age units. And you'll see these faint lines, but sort of ignore those for the time being. And here's that same area with an orthophoto, and you can see some of these geologic units that really stand out. This is a very unique green sand unit, but you can see this unit right here is kind of vegetated. And if you put it into LiDAR or the hill slope, you can see there are actually many more faults than were originally mapped. There's about a dozen faults there or so, 10 faults as opposed to 2 that were mapped. And so you can add some value. We know that Barnes really got us off on the right foot, knowing that which units were there. And we know how to map in particular this unit. And we know that there are faults there. And we can see them actually crossing the river even in some places. Things that they really couldn't see because they didn't have access to the LiDAR and the slope maps and the orthophotos. So we spend a lot of time adding value to some of these published maps. But we also have the benefit of some really interesting tools, things that I'm really just learning about. And again, probably old hat to a number of you all. So some of the drone work, that's kind of all the rage. You can really do some quick and easy images for analysis or outcrop modeling. And so here's John Andrews here flying on the James River out in Mason County. And so here's I think that's me, and John was flying the drone. But you can see this, outcrop is really just amazing, and so that drone gives you a perspective that you just don't have otherwise. And so you can start to annotate things like that. But and that's really useful for maybe structural analysis or trying to just understand generally the structural style for your mapping. But what we're doing now, and again, I'm just sort of nascent to this, but others are much more advanced, is that you can use photogrammetry to make 3-dimensional models. And so here's just a screen capture of that same, here's that fault right through there. So you can essentially take the outcrop home. You can quantify once you create these models, the thicknesses, the dips. There's software that you can actually, measure the orientations of strikes and dips and the fault orientations. You can create ortho images from them, and then you can even archive these. There are places to do that. And so more and more, we're looking at this as a tool to sort of supplement, some of the mapping. So I'm sort of jumping into some of the highlights of things that we're doing, and by far it's not, it's not comprehensive, but we try to integrate borehole geophysics where we can, where we have a question about what units are in a certain fault block, for example. We'll run geophysical logs, and so that's helped tremendously. A recent example of that is again back in the Dolan Creek area. That cave, that bedding plane cave is actually right here that I was telling you. But we logged some wells, and so we have a gamma count, a high gamma kick that corresponds to this argillaceous limestone right here called the Burt Branch member, and that's really a major lithostratigraphic boundary. So this at the base of it is separating 2 formations with this member defining that unit. So that's the borehole geophysics has been really important. And this, by the way, is also a structured for motion model. It's helped us to analyze that outcrop. Another interesting recent phenomena that we used is passive seismic. And I should say this is Jeff Paine. He's a geophysicist. I'm not. But I was showing y'all mapping some of these terraces using LiDAR, and you can see clearly this is a LiDAR image with some hill shade, and you can see these big terraces. There's some big springs right here. And so part of the question was, we weren't sure if this terrace was what you call, I guess, a strath terrace. That is, bedrock is really shallow, or is it really a cut and fill? So that terrace is a really thick deposit. And so Jeff used passive seismic to determine, and that's basically you put this little, it's a blue box, not a black box, but you sit it there and you walk away for 10 minutes, come back, and you get, it just uses the passive seismic energy that's ambient out there to give you some reflections. And so he's able to determine that there's over 6 meters of so we think this lower boundary of fill until you hit a big reflector at 6 meters. So those are some of the things that we're using to to help us understand some of the mapping and so forth. So looks like we're winding down here. So I just want to leave you all with some key points here. I guess, and again, these are probably things that you all completely have sort of come to realize, but really field geology and digital map database production are now sort of one and the same. They're integrated. You have to go out in the field for sure, make a geologic map, take observations, but you also really need to integrate that with the GIS work and your base maps. And it's a very much an iterative process. And that really maps are now map databases. And those databases are built according to the USGS GEMS, Geologic Mapping Schema, that was published in 2020. So that's this kind of big shift now that every single state survey, if they're and I believe all of them are participating in state map, are now creating these map geodatabases that have been standardized. There have been elements of maps that USGS has standardized for years, but this is the first time a database related to maps has been standardized. I think I'd also like to say that LiDAR is really an essential base map element for mapping. And I couldn't map what I'm doing now without LiDAR, and certainly in GIS as well. And, there's a lot of these things that are sort of take for granted. I've hardly said the word GPS, but, we can walk out with our phone and know where we are, reasonably accurately. It's really pretty amazing. Kind of speaks to the new technology aspect here of that bullet. The smartphones, the structured for motion models that we can do, and certainly the geophysics, all of that really enhances the detailed mapping that we're doing. And these maps are no longer static, and they're really dynamic, and they're meant to be evergreen. And so, these maps are no longer, we print them out and sell them at a certain scale, but really these maps allow us to make, scale irrelevant is what I'd say. So, I didn't really have anything to add here, but I would say that, I definitely have some challenges for making maps. And, one thing, it's a very compressed time frame. So, to do all these sort of 4 phases within a year's time frame is pretty difficult. You can imagine why. I mean, one of them is just land access. If you have limited access, it can sort of hinder your ability to interpret structures just from remote sensing data. You really need to get boots on the ground to be able to understand what it is you're mapping remotely. I would say peer review is kind of a challenge as well. And now we're producing open file maps which undergo a certain level of peer review, but they're not deeply peer reviewed documents. And so with this compressed time frame, it's difficult to get field review. And then also the map review is also very compressed. And so that's a challenge. The final layout of these maps, GEMS doesn't prescribe any of that. It's really just a database. And so the final layout itself, I think the states would be well served to have some standardization there. How the map looks, the color schemes, and granted, the USGS has a lot of that, but a lot of that hasn't trickled down to the state surveys. They kind of do their own thing. Another challenge thing is when you're in that sort of editing phase, when you find an error or something you'd like to change, does that edit get put back in the database? Because they're often spit out, these vector files are spit out into Adobe Illustrator, and if something needs to change there, does that make it back? And sometimes not. And then lastly, I'll say data archiving is kind of a challenge, but I'll tell you what I'm doing, and that is, I'll put it there. The Texas has a data repository as well as it's a dataverse, and so I think most states or universities have some branded version of a dataverse, and so there you can put all the GIS files, you can put all the theses that went into making that, you can put in the base map, the LiDAR, you can your field photos, field notes. everything, and you can archive them here. And that's one thing I've been doing. And that's not necessarily prescribed anywhere, but it's just something that I'm doing, personally. So, so with that, I think I have time for some questions. Okay, good. I'd write it about 45 minutes. And
there are a bunch of questions in the chat, Brian. So
okay.
Click on the chat button, questions and comments. So.
Okay. Let me see. One of my monitors died on me halfway through, so
yeah,
I can't see my screen.
Yeah, we can read them out for
Okay.
you, Brian.
Yeah, if you wouldn't mind, I can't.
You bet. So some of the comments, John.
Yeah. Okay. So
You want to? Okay.
the first is the comment. I worked for the Bureau back in the days when Chip Grote and Bill Fisher were directors. That's Johnny, and I can't see Johnny Johnston III.
Okay.
The next one is another comment from Johnny Johnson saying, we had a state map program at the Louisiana Geological Survey for decades. Richard McCulloch, a UT graduate, and Paul Heinrich ran it. And then John Woosley asks, what data is being used for the DEMs?
So the digital elevation models, primarily we use the LiDAR. And so that can come in different sort of resolutions. And that's, I think most of what I've been using is about, 1 meter in resolution. So that's essentially an elevation point every square meter. And so from that, they'll create the digital elevation model of the surface. And because it's LiDAR, you can filter out, the different wavelengths, some that would bounce off the vegetation, but some go through the vegetation and back up. And so that's, if you use those wavelengths, those data points, then you can create the so-called bare earth model. Right.
And these 1 meter data points, they're coming from aerial photography, photogrammetry?
Are you talking about the LiDAR?
No, not the LiDAR, the base map, the DEM.
Well, so
is that LiDAR based? Or?
Yeah, so the DEMs, the digital elevation models, there are ways to create those, not just from LiDAR, but we primarily use the LiDAR for elevation data. It's a digital elevation model, but you can, and you do for photogrammetry, create essentially a digital elevation model. It's just not as well constrained, that there can be a shift of 8 meters in elevation, for example, for a structured for motion photogrammetry model versus LiDAR.
Oh, really?
Yeah. And so what you have to do is you have to pin them down. So you can create your structured for motion model, and there's a term, and I can't remember in the software, but basically you say at this point on that photograph, this is the X, Y, and Z, and you can use several points, in an area, and that'll force it to go back into real space. So it'll be close, but it's not perfect. You really need to correct for that. So yeah, so we don't use DEMs often from those, although for an outcrop, it's usually really good. We use LiDAR from that. Yeah. And LiDAR is flown, it's aerial. So it's not from drones and not space. These are airplane flown LiDAR systems.
Because there's been some ortho photography flying for many, I think several decades now at 1 meter resolution too.
Yeah.
Okay. From Roy Schlemmer to everyone, are soil survey data incorporated into the BEG quotes new maps?
That's a really good question. I have pulled in, you can go to the soil survey, and you can actually get all the GIS files now, and it'll create a little geodatabase, and you can pull those in. And I have been pulling them in certain areas where I don't have good control, either from an existing geologic map or what have you. So I have definitely used those as one of the data sets, to supplement the LiDAR, the aerials, existing maps. Those are definitely useful in some areas. Some areas, they're not as useful. And so you just have to kind of get a feel for it.
Mhm. But they're not routinely incorporated in this map series.
No.
No. Okay. Next question. Can we get information about mineralization from LiDAR? That's NASA Hasway asking that.
Yeah. Yeah, it's definitely out of my toolbox, but you know, there's all these cameras that they go out and can look at different wavelengths, and they can see, you know, reflectance, and they can interpret that to be, you know, hematite or, you know, different minerals. So there's a whole classification and field out there, and the Bureau is looking at that, and not me, but others, for example, where they're trying to map the rare earth elements and some of those mineral resources. They're looking at some of these specialized cameras and systems to be able to map that. So yeah, that is possible. Yeah, the LiDAR itself, it is not, you know, used for that. But
I would say to NASA that is in my toolbox. I've been doing mineral exploration using multispectral imagery for something like 40 years. And more recently, we've had hyperspectral imagery from both space and aircraft, and even drones these days. That is really what you need for mineral exploration, because you can map alteration and all that sort of thing directly. On LiDAR, if you're working in an area where minerals have been exploited with what we nowadays call, what do we call it? This casual mining, you know, one man and his dog going out to have a mine.
Yeah,
that will show up really well on LiDAR. And so
sure.
you know what you're looking at, you can use that kind of information and integrate it into your search. John Johnson. Oh no, he's just wants a certificate. Reifert is asking, is there a process for verifying the maps?
Verifying the maps.
Peer
good
review,
question.
and you did touch on that. Yeah.
Yeah, you know, the peer review, more of that would be good. These are considered open file maps, so they're considered evergreen, and so the next phase of these maps would be to go through a more rigorous peer review process.
Right.
And so then they're published as a, you know, higher level. They call them miscellaneous maps at the Bureau, but a lot of the state surveys have those types, that sort of hierarchy of publications. And so this is really that first level. And there is, you'll notice all my maps, I typically have at least one, if not two other co-authors. Partly that's a scheme for me to get them to provide peer review and get out in the field, and also because they're knowledgeable and I learn from them. But between, you know, the three of us, we can hopefully catch most errors. But yeah, it's a good question.
I had a related question. If outsiders can come in and modify these maps, which sounds possible from what you're saying, is there a way that contributions from other people can be recognized and, you know, identified, and
that's the beauty of GIS is there's all these attribute tables, and so the data source can be attributed to where it came from. So it could be an individual or an agency or whatever, and even in all the metadata that's generated with this, I didn't even touch on the metadata, which should be its own category. You know, it's data about data, and that's kind of, anyway, a whole nother topic. But in there's the opportunity to acknowledge and cite, and then even when I take it to the Dataverse where I have there's yet another opportunity to acknowledge and cite sources. And so yeah, I think there's a lot of opportunity there for that.
And then Andy asks a somewhat related question. For literature references, how are the new database style maps being cited in report bibliographies as references, as compared to the old days when you could mainly reference, for instance, a topo quadrant date?
That's an excellent question. I think I don't have an answer for that. That very question is being talked about all the state surveys now. I participated in a meeting, and the USGS was they were asking just that. You as a state survey, are y'all publishing the database as its own thing and then the map as its own thing? So Texas right now is not publishing the database. So you would cite the map. But like I just put all these databases up on the Dataverse, so that generates a DOI. And so that could be something that's cited, it would be a sort of a date, I think, associated with the way the Dataverse works. So yeah, good question. I don't think it's been fully, sorted out.
And then here's a question for Wendy from Richard Howe. Will this presentation be available for download, and is it possible to get a copy of the PowerPoint?
Yeah, no problem.
Yeah, okay. Good. Then the next one is, can we work with a DEM resolution more than 1 meter? And I'm not sure what the questioner means, whether he means, coarser than 1 meter or finer than 1 meter.
Yeah, well, both are possible. I mean, you kind of go with what you have. There's some areas where I have a 0.5 meter resolution that, and the files get big, so, but you can see quite a bit. You imagine, 0.5 meter, 1.5 feet of resolution throughout. It really creates a detailed model, and you can follow individual beds.
Right. And then Richard Howe again asked, what is the accuracy of the smartphone in the field? Is it sub-meter?
No, it's not. I do check it. So often what I'll do is, I used to carry a GPS, but I tested it against just a handheld sort of recreational GPS version of my phone, and those are essentially the same. What I'll do is, if I'm taking waypoints, I also take them at known locations. And when I email sort of the data back to myself, I'll even go so far as to open it up in Google. And if I feel like, it needs to be adjusted slightly, I'll do that. And so, so yeah, it's not, but for what I'm doing, I've been able to achieve pretty good accuracy. And I'd say it's within 10 to 15 meters pretty consistently when I have a good open sky, good signal.
Mm-hmm. And then John T. Pop asks some excellent information and presentation. You hinted at following the data from technical to the graphical. Do you oversee a team of specialists?
I think they oversee me, is that the way that works. I wish we did, but there is a graphics team at the Bureau. So we kind of go through our process, and I did a lot of graphics, and so I essentially hand them a sort of a near closely finished graphical map, and then they tweak it, change the colors and the line weights according to what they want, and so then it kind of leaves our realm, and then and that's where sometimes the graphics can introduce errors. That's just the nature, and let alone my own errors. And so that's kind of one of the challenges I was hinting at is errors that can be introduced in the graphics process, but if something is caught, being sure that is sort of conveyed back to the database, the original database. That can be a real problem, but it's not a big team. It's a pretty small group at the Bureau. There's like 4 of us mapping, 5 of us, 6 with part-time help. So, and then we have some graphics folks as well.
And then Bill Turner just wrote radial arm displacement, and I'm not sure what he means. Are you there, Bill? Can you say what you mean there? Oh, no. Anyway.
Sounds painful.
Michael Sheehan says, have you had any experience with QGIS and QField open source free GIS tools?
Yeah, years ago I started playing around with QGIS, but then sort of got into the Esri world, and really the GEM schema, the US Geologic schema, is all geared towards the Esri world. So when you finish a product and you spit it out, it does have you archive, some generic GIS type files that other programs can certainly consume and use, but like shape files. But no, it's not geared towards that. And yeah.
I have done quite a lot of work with QGIS recently, Michael. This is John Berry speaking, and I haven't used QField though. But if you want to contact me through email, we can discuss those sort of questions. Janine Mausberg says, "Are there layers you can turn on to show soils information?" I guess you've answered that already.
Yeah, I mean, just in a generic way, you can really put in anything you want to into the map and then use it for your mapping. So I could have, I often do, I have a layer of soils and, showing the soil distinction, and I'll have the DEM, I'll have a hillshade, I'll have a slope map, I'll have these various, data sets that you can use to help in your mapping. So, yeah.
And Bill Agee says, "Are you using GEM standards for subsurface maps?"
That's, no, this is a short answer, but ultimately the initiative for the USGS is to make three-dimensional geologic models of the whole United States. So the first step was really to get our 2 dimensions, in good order and getting some standards there. But they're moving towards the 3rd dimension, and so they will have to develop standards for that purpose. And so I think it's coming, but right now I've got my hands full with just the 2D part. So,
yeah. And Reifert again says he studied under Brand Johnson at A&M and mapped a small set of faults on the Llano south of Mason, and then Brand followed up with a number of field studies.
Yeah, so Bran is a co-author on 3 of my maps. So I'm working with Bran, and that field map that I think I'd shown, that hand drawn, that was direct from Bran, and maybe some of those were your data if you worked with Bran out there at A&M. So yeah.
So, and Bob Keir says to everybody, Bob Keir is my age. He's getting on. So, having mapped in eastern Pennsylvania, Canada, and Texas for the Geological Atlas project, the Brownwood sheet and the Wichita-Lawton sheets, I am blown away at how the work is now being done. Wow.
Well, it's I often turn to Bob's volumes, and he's produced a whole lot of amazing geologic work. And so, the DNAG volumes, and, I've gone out and tried to educate myself on these different stratigraphic intervals. So really appreciate all your work, Bob. And we've got big shoes to fill, and, these really interesting tools and data sets that are fun to work with.
Yeah. Richard Howe says, excellent topic, excellent presentation. Thank you very much. Chris Kravitz says, can you describe the platform for gathering the field data and bringing your field map to the field? A normal cell phone, high-end cell phone, tablet, high-end GPS?
Yeah, no, it's literally just my phone right here. You can't see it. Oh, there it is. So I do have a tablet, but I find that, so it really just a normal smartphone. It doesn't have to be an iPhone necessarily, but that's just what I happen to have. It's the tablets, when you're bushwhacking through over hills, and having tablets and stuff is just, I find it kind of clunky. And then ultimately the phone works really well, very compact.
So Janine Mausberg says, great presentation, great information for us senior folks that are no longer working in the field doing mapping projects. Very cool to see how things are being done today. Andy wants to know about certificates. Yes, Andy, they will be automatically sent, I think, but you better ask. Put a note in the chat here. Excellent presentation from Angela Nabel. Richard Howe, how about Global Mapper? Does it follow the USGS schema?
So they don't. So the scripts that they developed and the database is really all Esri based. But I have colleagues that use Global Mapper quite a bit, and they really love that program. So I think eventually USGS will be forced to sort of develop, the schema that works with other software platforms.
That's interesting because I've had a bit of experience with those sort of things too.
Yeah.
Thanks, Brian. NASA Hasway. Thanks, Brian, for interesting presentation. Kathy Duran just reminding everybody that we have a new process for certificates. They're sent by email. Paul Warren, can any of us in the public get access to the shape files that are produced and published for this mapping project?
Yeah, I think you can just request it from us, but right now we don't have a good vehicle for distributing that like other surveys, other state surveys. I think that's going to change in the future. So now I would just send you a link to that archive Dataverse, and you'd be able to download the shapefiles and then some. Actually, quite a bit of stuff. So,
and then John Johnson, great talk. Thanks you, Brian. And Catherine, to everybody, very interesting. Thank you. Beautiful presentation from Bright Osuagu. And I think that may be the end of the comments. So
okay, good.
Anybody else, does anybody else have a comment? If you do, please put it on the chat quickly or open your mic and ask us directly. Nobody there.
Yeah,
Nobody.
no, I was more questions than I thought. But
it was a good one. It was a good block, wasn't
it? The last question was, can the recording be emailed? So I'll let y'all answer that.
Yeah, so Brian, if you can either give it to John or send it to me so we can post it on our website,
absolutely,
resources page, that would be awesome.
I'll do that.
I'll send it, Brian. I've got it.
Oh, okay.
Well, you have an earlier version. I think I tweaked it a little bit. John, I'll send you the latest version.
Awesome.
And with that, I'll have to thank you all for inviting me, and I enjoy talking about it, and happy to follow up with anybody who's interested and learn more, or send them data or challenge me, peer review my maps. I need some peer reviewers. So thank y'all.
That's awesome. Thanks, Brian.
Thank all the people who said nice words about the talk. That was very good. So very appreciative. So we're 7 minutes over, so I think it's time to shut it down. Thank you very much, everybody.
Thank you. Take care. Good evening.
Thank you. Take care.